This unit is on inverse trig, and the first topic is, it's basically an introduction of sine, cosine, and tangent. The first thing that I want to talk about is notation. So for inverse trig, you can see it written in one of two ways. You can see the superscript -1, or you can see an arc in front of your non-inverse trig expressions. So the superscript, sometimes we get that confused with the reciprocal. However, the reciprocal does not have the -1 in between the function and its input value. Instead, the reciprocal is when you have the entire function or output raised to 1, which will, properties of exponents that will move it to the denominator or flip it, okay? So if we were to think about this for sine, if it was the reciprocal, the entire trig expression would be raised to the -1. And then this still gets a little confusing because in the calculator it might look a little different too, but this is why I typically use arc in order to differentiate between the two. However, you do have to get used to both because you will be exposed to both. So just remember that this is not the reciprocal. Because the reciprocal for sine would be 1 over sine x, which is equal to cosecant x. Okay. So the next unit is going to be trig identities and then trig solving. We're going to start seeing non-inverse trig expressions and inverse trig expressions within equations. So make sure that you get used to this notation, okay? So the first thing that I want to look at is the period for sine. This has 2 periods, but I want to focus on just this one, from -pi to +pi. So if you recall from Algebra 2, an inverse is when you switch the input values with the output values, okay? I don't know why I drew a linear function. What I wanted to do was draw this, okay? So if we have f of x is equal to y, the first step that you would do is switch the input with the output, so you end up with f of y is equal to x. Now that's where this notation comes into play, because the inverse is going to have the outputs of the original function as its inputs, and then the outputs of the inverse will be the inputs of the original. So it gets a little confusing, but with trig, it's a little bit easier because they are very different. The inputs for trig expressions is an angle, or theta, all right? So either in radians or degrees. The output for trig expressions is your coordinates. So either x or y, or a combination of the two, y over x or x over y. So for inverse trig, these will switch. These will become your inputs, which are the coordinates, and then theta will become your output. So inverse trig will follow the same rules and restrictions as functions that you talked about in Algebra 2 and that we talked about earlier this year, okay? So the only thing that's really different is that our inputs are now angles and our outputs will be the coordinates, but they switch. So now the inputs will be the coordinates and the outputs will be the angles. But before we talk about evaluating, let's just talk about where are we going with these. So to get graphically, to get the inverse of a function, we reflect it over y equals x. Whoops, let me get a brighter color. Y equals x. And when that happens with our sine function, we're oscillating to positive infinity and negative infinity. But if we just restrict it from -pi to 2pi, we end up now oscillating up and down instead of left and right, okay? So this poses a problem because now we are not able to evaluate because for each input, there is more than one output. And before we talk about that, let's talk about the inputs and the outputs. So if I start here, this is going to be -pi, -pi, and then we have an output of 0. So if I think back to Algebra 2, I switch my inputs and my outputs. That will transform me to my inverse. So we'll call this the inverse of f of x, and f of x will be sine. Okay, so this is also inverse of sine x, or inverse sine. So when this happens, we are also switching the input and output, okay? And when those switch, it also switches the axes. So in my first graph, the horizontal axis is theta, and then the vertical axis is going to be our outputs. And for sine, this says x, so we'll just go with, actually that's the input. So we'll call this vertical line f of x because that's what the output is labeled as. Technically, it will be y on our unit circle because sine is going to be the y coordinates. When we go to the inverse, the horizontal axis is now f of x, which is our y values, and then the vertical axis will be theta. Okay, so everything flips from your inputs to your outputs, the axes, and then also domain and range, but we'll talk about that in a second. So if I start with this negative pi 0, I want to sketch 0, negative pi. So I'm going to start at 0, and then I'm going to go down to negative pi, which will be right here. So this is 0, negative pi. So horizontally, I'm staying at the origin because it's 0. And then because my theta is now my vertical axis, I'm going to go down pi. Now the next coordinate point on here is negative pi over 2, negative 1. So now I'm going to flip those. So I end up with negative 1, negative pi over 2. So on the horizontal axis, I travel that y coordinate, which is negative 1, and then I go down negative pi over 2. So that will be here. And if you notice, when I connect this, the concavity is opening up to the positive horizontal axis, just like it did over here. It's opening up to the positive vertical axis. So I have my concave up here, which is concave towards the positive outputs. This is still going to stay concave to the positive, what are now the inputs. But if you notice, it's concave towards the positive y values, same as the original function, concave towards the original y values. And if I continue this trend, we have 0, 0. So I end up at the origin, and then I continue that concavity. And then the next point is pi over 2, 1. So that becomes 1 pi over 2. So I travel over 1, go up pi over 2. And now my concavity is switching because on the original function, we are now concave down or towards the negative y values. And then on my inverse, it will be concave to the left towards the negative y values. And then I can finish connecting by graphing what would be, this is pi and then 0. So it would be 0 pi on this one. All right, so even though I'm now ignoring all of this, I'm only worried about this one period, I still have a problem because we're not supposed to say vertical line test, but it doesn't pass the vertical line test, aka in College Board terms, for each input, there is not exactly one output. So if I were to plug in even just 0, we have 3 possible outputs, and we need a function. We can't do that. So this did become restricted, and it was just a choice made. They were evaluating or using these inverse trigs, and they're like, we need to have a function. So what was decided was that we will restrict and only use this, okay? So we are going from negative 1 to positive 1, okay? So your inverse sine function only exists within this realm of possibilities, okay? And then this next picture just stretches it out a little bit. So this coordinate here, so we're stretched from, oh, this is for sine. Okay, so this is going back to the original function. So if I were to scratch out what we restricted, it would be here. So my original sine function, I'm only worried about this middle part here. So it would be from negative pi over 2 to pi over 2, which would be the vertical axes on this one, on my inverse. But for my original, it would be pi over 2 to negative pi over 2, and then it oscillates between 1 and 1. So if we take the inverse, we're going to end up going from negative 1 to negative pi over 2, and then 1 to pi over 2. And if you notice, sine passes through the origin, it's increasing, and it goes from concave up to concave down. Inverse sine is going to also increase, but it's going to go concave down to concave up. And then let's go ahead and notate that this is positive pi over 2, and then this is negative pi over 2. Now for inverses, everything is flipping, so that also includes the domain and the range. Now before I go to the domain and range, I need to show that now that this function is 1-to-1, we can use it to evaluate. So we can use it to evaluate multiple types of coordinates and get an output for the angle as long as it fits within the domain restriction. So the domain for sine of x, it is usually all real numbers, but with this restriction, it is now going to be negative pi over 2 to pi over 2. And I'm using the restriction that I had on my inverse sine. And then the range is going to be negative 1 to 1. That didn't change. The range for sine is negative 1 to 1 anyway. So for inverse functions, the domain and range will switch. Oops. So now the domain for inverse sine or arc sine is going to be negative 1 to positive 1. And just to be clear, those are your y values. Those are the y values on the unit circle, which is why if you think about the unit circle, and think about the y values, negative 1 is down here, positive 1 is up here, which makes sense for our range to be from negative pi over 2 to pi over 2. Now, these are your angles. Now, that does mean that 3 pi over 2 does not exist, all right? Because if you remember, for a standard angle, it has to open up and stay connected. So once we get to pi over 2, we have to stop. There's no other possibilities because we needed this inverse sine function to be 1-to-1. So if we go past pi over 2, it's no longer 1-to-1, which means we can no longer treat it as a function. So if we want values in the fourth quadrant, we open up in the negative direction, and then we can only go to negative pi over 2. So it is limited with the values that we can use for this, but there are still some great applications that we can use for inverse trig, which we'll see in later units. All right, so for cosine, we weren't provided the sketch, but we can draw a quick one. So we'll draw a quick sketch of cosine. So we'll go from negative pi to positive pi. And let's just draw a period. Again, maximum is 1, minimum is negative 1. And we'll go from here, cross through the axes, and come back down. And then remember, we want to go concave up, concave down, concave up. So we have one period of cosine. Go ahead and label it as cosine x. So for inverse cosine or arc cosine, we're going to switch the inputs and the outputs. So now I'm just going to take my angles and I'm going to apply them to the vertical axis. Whoops, that should be negative. And then I'm also going to apply my outputs, which so these are our x values, negative 1 and positive 1, because cosine is x on the unit circle. So my horizontal axis will be the x values. So we'll say x values. And I know it's a little difficult because in non-trig functions, x is always the horizontal axis, but these are our outputs for the unit circle. So therefore, the outputs will now be the horizontal axis or the inputs. The vertical axis are our angles, okay? And that means outputs on unit circle, not outputs for the inverse trig. So they will now be the inputs for inverse trig. And now angles are outputs for inverse trig. So I need to keep repeating that the output or the result of evaluating an inverse trig expression is an angle, okay? All right, so if we sketch this, we can switch our x and y coordinates. This is negative pi, negative 1. Therefore, on inverse cosine, it will be -1, -pi. So we'll be down here. It looks very similar. The next one is going to be -pi/2, 0. So we'll be at 0, -pi/2. And if I follow the trend of the curve, so I have, this is opening towards the negative outputs. Therefore, it will open towards the negative inputs on this graph. So this is concave up. Therefore, it will be concave to the right, concave towards the positive. And then once I go past -pi/2 to pi/2, that's going to be concave down or towards the negative values. Therefore, it will also be concave towards the negative values for my inverse. And then we're going to end at pi -1. If I switch that, I get -1 pi. It's concave up towards the positives. Therefore, it'll be concave towards the positives. Now, if you're in my class, you will not be expected to sketch these. We used to in honors pre-calculus where you would have to sketch and even transform them. But with the added topics from AP, we had to remove some things. And since you are not expected to sketch on the AP exam, we went ahead and removed that expectation. Now, there are some units where we do have you sketch, but this is one of the ones where we took it away. It's more important that you know how to use them and evaluate them and solve for compositions, okay? All right, from here, again, we fail to pass the vertical line test, aka for each input, there is not exactly one output, okay? So again, we have to restrict our domain, and the choice was made to use this. So we are using this positive curve up here. Now, there's a sketch of cosine x, so if we go back to our sketch, we end up excluding the negative angles, which means we exclude the negative angles as outputs over here. So this is all we're using for arc cosine. And again, that makes this 1-to-1. Therefore, for every input, there is exactly one output value within this restricted domain. So this is a picture of cosine. So remember, the rest of this looks like this. But with that restriction, we are only in this part of the curve, okay? And now it is 1-to-1. So the domain for cosine without this restriction is all reals, but in order to make the inverse a function, we now restrict it from 0 to pi. So if you look, we go from 0, 1 to pi -1. That domain or the angles, the only angles that we can input into cosine with regards to the inverse is 0 to pi. And then the range doesn't change. It's still -1 to 1. Now for inverses, domain and range switch. So now the domain for arc cosine is going to be -1 to 1. That's all we can input. And the output will be 0 pi. So now if you think about the unit circle, if you think about the x values, +1 is here, -1 is here. And with that restriction, we chose to go from 0 to pi. So we are only using this part of the unit circle for arc cosine. And we'll talk more about that in the next topic. Tangent is the last one for today. So if we do a sketch of tangent, again, this one is very unique because of the vertical asymptotes. And those vertical asymptotes, if you remember, they come from what the result of a tangent expression is, and that is y/x. When we take the ratio of those sides, there are values where x is equal to 0, therefore it's undefined, so we get vertical asymptotes, okay? Cosine and sine, they don't take the ratio. It's just one value. Okay, there are some ratios like √2/2, but none of those ratios have a 0, so therefore we do not get a vertical asymptote. It's just an oscillating function. All right, so for tangent, if you think back to what the parent function for tangent looks like, we have our two vertical asymptotes and then 3 key points. We have a vertical asymptote. Do an equation, x equals -pi/2, and then the other one is at x equals pi/2. And then this point here will be -pi/4, -1. So we'll put -1 on our vertical axis. We pass through the origin again, like sine. And then here we're going to have pi over 4 positive 1. And we'll add that to our vertical axis as well. So, of course, tangent does go on forever in both directions, infinite number of vertical asymptotes, but we're going to focus on one period. So this is tangent x. Now, if we go to the inverse tangent, we are going to flip everything, all right? Switch your inputs, switch your outputs, domain range, all that good stuff. So my horizontal axis for my non-inverse trig expression had negative pi over 2, negative pi over 4, pi over 4, and then pi over 2. So those are going to be switched to my vertical axis. So below, I will have negative pi over 2. The next value is negative pi over 4, and then 0, and then pi over 4, and then pi over 2. My horizontal axis will have my output values, which is the ratio of y over x on the unit circle. So we'll have negative 1, positive 1. So again, that horizontal axis is the y over x. When for our y over x, it was the vertical axis. The inputs are thetas, which means now the outputs for our inverse trig will be theta. So if you remember, whenever we have a function with vertical asymptotes and you take the inverse, those vertical asymptotes become horizontal. They stay with negative pi over 2 and pi over 2. Now, without any restriction, this would go on all the way, up and down in both directions. And then again, we don't have a function. It's not one-to-one. So they had to create they as in mathematicians created a restriction, and we kept it around the origin, which is nice, all right? So we kept it at negative pi over 2 and pi over 2. And then if we look, we have negative pi over 4, negative 1. We're going to switch those, so we have negative 1 and then pi over 4, or negative pi over 4. So we'll be down here. And if you notice, or if you remember, tangent is monotonic. It's always increasing. And we see that it's increasing towards the positive values. It goes from concave down to concave up. So arctangent will do the exact opposite. It still will be increasing, but it's going to be increasing where it's concave to the left and then concave to the right. And it's still approaching those horizontal asymptotes. So this is what arctangent looks like. So now if we look, every single input has exactly one output for all real numbers, okay? Because it does go to infinity in both directions. So this is a sketch of the original tan, the non-inverse trig expression. And this is the only one where we can actually use the domain and range. Well, not exactly, but closely. So the domain for tangent, it was all reals. Well, no, I'm getting myself confused, switching back and forth. The domain for tangent used to be x cannot equal pi over 2 plus pi k, okay? And that was because we had an infinite number of vertical asymptotes. But now that we are restricting it so that it is a one-to-one function, aka restricting for arctangent, that is no longer the case, all right? We actually have a closed interval. And I just lied again. It's not closed. Well, it is, but it's non-inclusive because of those asymptotes. So the domain for tangent with this restriction is negative pi over 2 to pi over 2. And then the range is still all real numbers. So again, for inverses, we will switch, which means for arctangent, the domain is all real numbers. And the range is going to be negative pi over 2 to pi over 2. So even though the inputs are all real numbers, we are still going to be restricted from negative pi over 2 to pi over 2, just like sine. So arcsine and arctangent have the same restriction in quadrants 1 and 4, and then arccosine is restricted to quadrants 1 and 2. And we will talk more about that in the next video.